So it's close to 2, maybe we can begin. So good afternoon, everyone. Welcome to this monthly featured webinar series of the Digital Surface Manufacturing Network Plus. We have a distinct speaker today, and it's my honor and a great pleasure to introduce him to this session. As such, I feel he needs no introduction as a fellow of CIRP. Professor Rajkumar Roy is a well-known figure and a very distinct speaker in this and many other podiums he has been so far. So Professor Roy is the Dean of the School of Mathematics, Computer Science and Engineering at City in London. He's a distinguished academic speaker in leading the way for many youngsters, ECRs, and many settled academics, including myself now, while he had established through his vision the Through Life Engineering Services Center and this whole technology landscape while promoting the broad concept of engineering for life, culture in businesses and profession across various sectors. He is now devoting himself to develop what we can call it as a socially responsible STEM professionals who will drive the future, and especially in the UK at least. And he's currently leading his research in the area of self-engineering systems, which is going to be the key topic for today. As you can see from his title, that through life engineering to self-engineering is what we are looking forward to learn, together with Dr. Sam Brooks, who is also a faculty member at City University. So with those initial thoughts, I would like to welcome Professor Roy to this amazing session that we are looking forward to, and would like to hand over this session to you.
Thank you, Saurav, and thank you, Professor Alan Matthews, for inviting me to come along with Sam to give you some views on where we think some of the opportunities may be in what we call self-engineering. So before I start, let me give you my quick additional information about my background. I worked in industry in maintenance before joining academia in automotive sector. I was actually repairing machines that made cars. And since then, I developed some passion why machines break, why machines degrade, why components degrade. And that's the basis of research that what I'm trying to do over the last maybe 25 years or so. That culminated into a national center on through life engineering services supported by EPSRC as the main funder, and industry like Rolls-Royce, BAE Systems, Bombardier Transportation, and many others. And that was carried out at Cranfield University before I came to City. After joining City, I have been developing the idea of self-engineering as a follow-up from what we did in Through Life Engineering Services, where we identified that one of the big challenge is to increase life of components, subsystems, and then systems. And we could do that if machines could self-repair like animals. For example, you will see how animal world, biological entities self-repair part of their body, part of their activities on continuous basis. And that's how we have started developing this research. I'm working with Sam. Now Sam will introduce himself.
Hi, yep, thanks, Raj. My name's Dr. Sam Brooks. So I'm a research fellow at City University of London, working with Raj on self-engineering systems for the last 2 years or so around this area. Cool.
Thank you, Sam. So today, I'm going to share with you my thoughts And Sam, please feel free to join me. And then we will discuss existing work on self-healing, self-repairing approaches within coatings. Now, all these work are actually from other colleagues around the world. So it's important to note the references on those pages where we mention work from others. We have given clear references, and you can follow the paper in there. And through this process, I would like to conclude saying why self-engineering would be useful and what are the trends in self-engineering. That's what you can learn from this session. So let's start. My work in Through Life Engineering Services, or Through Life Engineering in general, started with a domain of manufacturing where we are working on not just product, but product service systems. You can imagine there are colleagues who are doing research to support servitization, like instead of buying a car, maybe we can buy service from the car, and the manufacturer remains responsible for the vehicle and its operation so that you can get uninterrupted service from the car. And you only pay per hour of the service. And by the way, this is real. This is already happening in many large cities like London and other places. Streetcar is one example of that, where you can pay £6 per hour, and that includes insurance, petrol, everything. And you can use as much as you want per hour. Now that gives additional responsibility to companies like Rolls-Royce, who are selling many contracts in power by hour mode, that how to increase life of components, how to increase, for example, mean time between repair, between MRO visits. That's what they are looking for, to reduce maintenance cost. And that's the premise where we all started in this journey. And self-engineering is going to take it to the next level. So that's why we are studying self-engineering now. So this was the Through Life Engineering Services Center. That was one of the national centers funded by EPSRC, Innovative Manufacturing Center. And that developed technologies along with the University of Durham, Durham University, and industry partners. We worked with aerospace, rail, defense, automotive, energy sectors in Through Life Engineering. So it's cross-sector applications. Rolls-Royce was one of the main partners in this activity. I'm continuing to work with Rolls-Royce in other projects around Through Life Engineering. And one of the things I did in this center is around degradation modeling. How does Class A aero components degrade over time? And we developed NDT techniques, mostly using thermography as a robust and affordable technology to implement inspection for components in MRO shops. That was the target for this. And we used the image, thermographic image, to understand level of degradation. That was my personal work, and there were a lot of other colleagues did other activities in this area. We currently have a platform grant in Through Life Engineering Services, which I was the PI before. Now, after moving to City, I've become COI, and we are continuing work in there. And that's where self-engineering fits in. There was a PhD student, Lawrence Tinsley, completed his PhD last year, where we looked at prediction of life of coatings, thermal barrier coatings, TBC coatings. And for that, we actually looked at service load and remaining useful life predictions. It was interesting that while applying thermography as a technique, we looked at change in apparent diffusivity of TBC, thermal diffusivity of TBC over time as a way to identify different stages in its life. That means how degradation, different levels of degradation is derived. And we try to understand that pattern. Now let's focus on self-engineering. By understanding degradation and trying to model them, one thing became very clear to me, that one of the research area we should be doing more is to make machines more resilient to degradation in the first place. So after working in my early years in maintenance, now I try to work how to remove maintenance if possible. Now I have to tell you that maintenance cannot be removed altogether. And we had lots of discussions about this in CIRP, which is the International Academy of Production Engineers, on continuous maintenance. Certain sectors like aerospace, generally, these are long life, expensive systems. They require continuous maintenance. Now, how can you reduce some of that is one of the things I'm trying to pursue at City University of London. And we call them self-engineering. Now, when we go into the detail of this, you will see that self-engineering is not new. There are a lot of things that already happened over the years, and I'm going to tell you more about that. So it's an ability designed and built into a system to independently identify any loss or potential loss of function and then automatically restore functionality fully or partially to maintain its availability. So maintaining availability is important for us, and that provides system resilience. Now, if we can reduce usage of material, that also have impact on sustainability because we use less resource as a result. We looked at mobility as a service, and there was actually a collaboration with HVM Catapult and Warwick Manufacturing Group. We produced a report. Anybody who is interested, if you are interested, you can actually find that report. I can send it to you. This is more market-facing report. But one of the things that came out in this, when we looked into some of these areas, what you can see here, especially under direct value added through life engineering services in mobility as a service. If you look at the small letters here on the right-hand side, my right-hand side, in mobility as a service stage 3, between 25 and 2030, we are talking about vehicles which are not just autonomous in driving, but also partly or to a large extent autonomous in maintaining itself. So self-healing of materials and technology becomes important. Self-repair where possible. I believe after spending few years in this area, not everything you can self-repair. There will be a degree of thing you can do in self-repair. So there is always certain limitations. And you can see that in the future, in MAS level 3, this becomes a key technology. Now, this is done about 4 years ago. And since then, I have been thinking about self-engineering as an area to develop where we can make a contribution in terms of understanding what makes a machine to self-repair. How can we, first of all, how do we understand what is it that contributes to that level of self-engineering behaviors? And then next question is, how can we engineer that into a system to give it the functionality? And that's what we are trying to do now. Sam and me, we are trying to do that now. And with a group of students. So there are other applications. For example, this is already going on in many organizations, self-healing of polymer composites. There are big research groups in universities around the world in composites repair through self-healing methods. You can see some example here, but it's also now being practiced or at least prototyped for reality in many companies. So the characteristics we are looking for in self-engineering, it must have the ability to restore or partially restore its lost function. It must be built into system. That means it needs to be built in, not supported from outside. There must be no human user intervention in the process. The aim should be to avoid or reduce maintenance, prolong life, and increase system resilience and robustness. And these are the words that's already being researched around the world. Self-healing, I have said a few times now. Self-repair is another major activity that's going on in this area. Other big areas are self-cleaning, self-optimizing, organizing, and then reconfiguration has become quite popular as well, whether it's a robot reconfiguration or other types of reconfiguration activities. We looked at how publication has developed over the years. You don't see much before 1970, so if you take from there, you can see here on my right-hand side, self-healing is the most common word used in this category of research. And this is mostly to do with material science. Self-healing is really, majority of the focus is material science. Then self-organizing. Self-organizing is quite popular in research groups. And these are the two areas that has really grown between 1990s and now. But if you take these two fast-growing areas outside the data, out of the data, then you can see other areas like, for example, self-repairing is the next. Self-sealing becomes important and self-adaptation. But obviously, sorry, self-optimizing is the next one. So first is self-repairing, then self-optimizing, and then we have self-adapting. But other things are growing much slower. And now we are talking about applying this in number of examples, number of areas. For example, in electronics, Durham, part of the National Center, Durham already applied this in FPGA programming and improving robustness of FPGAs. So that comes under self-reorganization of the network of cells within the FPGA. And electronics is one area where self-engineering is applied quite a bit. I see Ashutosh just joined in. Hello, Ashutosh. Ashutosh was also one of the co-investigator of the National Center, and he applied I would say organization, reconfiguration techniques into mechanisms. And you can see some of that is studied in the review paper. We looked at patents and what is becoming popular in patents. Self-organizing is number one when it comes to actual applications. And number two is self-sealing mechanism. This is very, very important for many applications, and then self-healing. So these are the kind of top three that's coming up. Now, when you look at self-engineering systems, there are two groups you can categorize in. Some are just natural instincts, no control necessary. It's like pre-programmed, and you can see that quite a bit in plants, in trees, in animals, primitive animals, where without any control, there is a mechanism that is triggered when a damage has happened, and it's fast, but it's very limited what it can do. It's very specific to solutions. But there are others, more advanced example, where you could see that there is a level of control. And in reality, what we have seen, that control is divided into two types here: local control versus central control, supervisory control. That's how we see self-engineering is manifested in many applications. And this could have some implications how we design systems in the future too. So you can see here in mechanical systems, self-healing materials and self-sharpening is quite popular. Civil engineering, self-sealing is quite a bit researched on and applied. And in electrical, as I mentioned before, Durham's work, it's quite a bit of self-reconfiguration work in electronics like FPGA, self-healing circuits. And then you have the whole domain of software, reconfiguring itself and self-healing itself. So that's another full domain which is not included here because we are just focusing on hardware-based self-engineering applications. Mechatronic systems, self-assembly is number one. And currently, we are also looking at biological systems. What can we learn from biology? When you do kind of broad research in this area, we can see that there are a number of examples which are very specific examples, just designed for applications. But what is lacking is common understanding. What is it that gives that behavior? And that's what we have tried to do in the first phase of this work. And next phase of the work will be to apply those principles to design systems. where we can demonstrate and fine-tune, control those behaviors. So these are some examples from other colleagues. These are work from others who have done self-healing materials. I'm giving this for your reference. Similarly, self-sharpening blade, it started back in 1803 in plows. But more research, more recent work in 2003 comes from Brunt et al. No, Brunt, Mechanical Innovation in Industrial Revolution Plow Design, and then self-sharpening mechanism for sea urchin. You can see here 2011 work. We just had a couple of interesting discussions in composites design and repair using self-healing and self-sharpening ideas. When there is a damage, how we can repair it, how we can restore shape, all of these questions. And that's becoming the latest thinking in some of these research areas. We look at, as I said, we are looking at bioinspiration in this. And there are plenty of examples, like wrinkling of our hand. This does not happen without central control, but it also requires local cells to behave autonomously. So it has local control as well as central supervisory control from our brain. And this is one example where we could give you direct answer about need for combination of local and central control to manifest some of the behaviors. If you go back to jellyfish, like moon jellyfish, reconfiguration is achieved purely by stress and strain forces. If they lose any limb, they can distribute their remaining limbs into a symmetric shape. So they change shape. But that can only be done by stress and strain as they're floating in the water. These are good inspirations. But I'm always asking questions. What does that mean in terms of general principles? How does it actually happen, and what can we learn from this? And then, for example, bone modeling is influencing additive manufacturing. Here is some example of that to repair cracks. But there are also problems. If we look at biology as inspiration, we should not take that biology is always right. Actually, there is quite a bit of problem with biological systems too, like too much redundancy. One of the things we all try to design machines for is how to make it, how to optimize it, how to improve the design so that level of safety is achieved, but with optimum amount of resources. And that often is not there in many biological systems. So that's part of the thinking that's going in here in this research. Just to understand complexity better, what we did, we took 5 self-engineering existing systems from publications, and we tried to break it down into what we called functional requirements and design parameters based on Namsu's axiomatic design. And that just to give us a premise to understand level of complexity involved in different components of these systems. One such system we looked at is vasoconstriction of our own body, blood vessels. How does it regulate temperatures? By constricting certain vessels and dilating others. And what's the role of central systems, central control systems versus local muscles controlling, without being directed by the central system? So we broke it down into FR, like you can see here some of the high-level FRs, then next level down, and then DPs. And that relationship between these two, which was then validated, gave us the basis of understanding what complexity is. Now, by going through this, we came up with 3 things that affects self-engineering fundamental behaviors. Redundancy plays a major role. And then you can have different grades of redundancy. Repeatability is extremely important. Number of possible repeated responses. If you just respond once for a change, so if a crack appears and you can only repair once in that area, that's very rudimentary repeatability. But you can, if you are able to repair the crack multiple times at the same place, then the repeatability increases with, in terms of complexity. Control is another aspect, self-control. And then that has 2 components, local control versus central control. Simple local control is the most rudimentary. But first is no control at all, and then hierarchical control. And beyond that would be emergent behavior, where multiple controllers are working together. So that's the kind of definition of drivers of complexity we have settled with after studying number of systems. And then we verified that with experts, and they, in majority, confirmed these 3 as the major driver, which is now becoming basis of some of the next work we are currently doing. We also looked at biological systems. In this case, we are reporting 8 cases, but actually we have done more. And you can see here, several examples, more than, 8 cases against students, how students then marked. So what we did, we looked at the scoring of experts, and then we also looked at scoring of novices. About 25 odd students were involved. And that gives us an understanding what's the level of complexity in biological systems. So we are trying to improve the understanding of self-engineering systems in biology as well as in systems which exist already, engineering system that exists already. In our first piece of actual system implementation, we have built a test rig to demonstrate basic concepts of self-cleaning. This is actually coming from any process sector would require similar challenges. So within the heat exchanger, there are fouling present that happens as the fluid passes through it. How we can clean it and build that capability within the system so that it's controlled and happens locally. We try to implement that within the system with some controls so that we can control the level of
Hello, sir.
Hello, can you hear me?
Yes, Professor, we can hear you.
Okay, so this piece of work, we have concluded initial set of experiments already in this self-cleaning system. And you can see here, we are now trying to control redundancy, repeatability, self-control, and seeing how does that improve efficiency of the cleaning itself in the heat exchanger. That's our goal in this very first attempt. Now we looked at some of the work, especially early work that's done in coating, because I thought it will be good. You will be interested to know what's going on anyway in this area. So this is nothing to do with our work, but we have done the studies, and it is part of our literature review. So this work is actually from Professor John Nichols back in 2002. That's when he started looking at this type of self-adaptation behavior with smart overlay coating. And some of the early work he did is quite interesting, because I came to know this when we were working together in the platform grant and before that in the National Center. This is about high temperature corrosion coating designed with chromium-rich intermediate layer. The reference is here. And essentially multiple layers which gets activated to give a stable protective oxide and protect temperature as a result. This is the early phase of the work that was happening from an EPSRC project John had. Other colleagues have picked up work on this, quite a bit of work on polymers, using polymers, capsules of polymers, microcapsules, containing PDMS or DMD-DNT catalysts. So you need a trigger. So temperature can be a driver, and then you can essentially melt the microcapsules and they give you the protection you need. And this is a very common approach nowadays, quite popular. And you can see that in construction industry with applications on cement, and also in composites. This is quite a bit of work is happening in Bristol in these areas too. Another very interesting work we saw, and that's back in 2020, so that's quite recent, where self-repair of Martial coating through friction. And this is not built-in activity. This is the other point I want to highlight. But this is one way people have started using repairing coatings. But here you need additional support from the roller, from the ball, in this particular example. Now, recently, well, 2016 work in Illinois, I think in the US, there is quite a bit of work on, I'm just finding the right word here. This is actually a protein from squid teeth. Yep, so I've got the right section here. Squid teeth is providing the protein which helps us to, in a way, repair wool fiber, wools itself or fabric. So it's about textile repair. And this is another coating cum repair technique that's used back in 2016. So ladies and gentlemen, what I have tried to do is give you an overview of self-engineering, mentioning its origin, why we wanted to research on self-engineering as a technique, which started from Through Life Engineering Services work we did a few years ago, and where some of the research is going both at City as well as externally. But one thing still needs to be done is manifestation of this at scale. Automating, integrating all stages of self-engineering systems is something not happening yet in larger scale. And if you look at self-engineering systems, we are good in monitoring, but taking actions, doing self-repair in a built-in with a built-in technology or resource is not well developed yet. Replication of biological mechanisms for repair and maintenance in engineering product, I think, is a real opportunity. We should be exploring more on that. But as I said already, that we have to be very careful that biological systems also have limitations. So when we get inspiration from biology, we should be challenging that and taking the strength of biological systems. More development of mechanical or physical self-engineering methods outside self-healing materials and robotics, because that's the two areas where there is more work already ongoing. Self-healing, it's mostly into material science, and robotics is essentially about self-reconfiguration. These are the two areas which is quite a bit of work already going, but other areas could pick up, including, I hope, this network can also contribute in accelerating research on self-healing and self-repairing coatings technology, surface engineering technologies. New design tools and strategies to help create and develop self-engineering systems for higher tier roles is also essential going forward. We need to actually have design rules, and then from that, tools that will help in designing self-engineering systems in the future. With that, I would like to stop, and I would like to invite questions. Me and Sam, we will try to answer your questions. Thank you.
Thank you so much, Professor Roy. That was splendid talk covering so many great deal of things, especially inspired from biological systems. And it was fascinating that this talk just came in time when the UK is seeing the right to repair. So because all of these technologies will be pivotal to support and accelerate the repair of products, especially electronic products, which is considered to be a huge waste. Because I was seeing a lot of self-related terms, and your talk was so intrigued. I was so intrigued with the talk that I was starting to imagine already that perhaps we are ready to think of self-sustainable systems now, which will require alliance of manufacturing, such as self-manufacturing through self-repair technologies, as well as self-reconfigurable manufacturing systems like robotics and self-healing materials. So it will be of course nice to work together with you through the DSM network in looking at these technologies. And floor is now open, so for the broad audience to ask their questions and doubts.
I think Ashutosh has raised hand.
Yes, yes, Raj. Raj, thanks a lot. A very, very interesting presentation and a lot of very interesting ideas there. I have two questions, Raj, and wanted to get your views on this. The first is around application of these ideas in manufacturing technology itself. So when you were doing your comprehensive review, did you see any examples where some of these were applied to machining, for example, or assembly systems, or any of those manufacturing process areas where we could use some of these ideas on a shop floor?
Okay, so very, very good point. I was actually looking for it. No, answer is machining technology, no, but we have seen reconfiguration in robotic systems. So okay, that's one, which could be used part of assembly systems. So assembly systems has more opportunity at the moment. I think from that perspective, remember my focus is really to apply this into repair, to restore functionality. Yeah.
Yes. Yes.
So if we take that, question I would ask you back, Ashutosh, is
Yes.
are you looking to
Yeah.
self-repair
Yeah.
a grinding machine which
Yeah.
has stopped working? Is
Yeah.
that what we are looking for?
Yeah.
Or we are looking to improve
Yeah.
self-adaptation of the grinding machine so that based on variability in the workpiece material composition,
Yes.
because the
Yes.
hardness changes, yeah,
Yeah.
should it continuously adapt through monitoring? Now that part of the work of
Yeah.
monitoring and then controlling the machining process is already happening
Yeah.
in
Yeah.
traditional manufacturing technology. Yeah?
Yeah.
What is not happening is the repair of the machines in a responsive manner or in even a proactive manner. I think that's the gap at the moment.
Okay.
Assembly has better opportunity through
Yeah.
reconfiguration angle.
Yeah. Yeah. Raj, just a follow-on question on this. When you consider the concept of self-repair, how do you define the system boundary there? I mean, is it so? If I take a machine tool, is
Yeah.
that machine tool all encompassing in terms of the self-healing capability, or would you consider that the self-healing capability may come from within the factory but outside the machine tool?
Yeah, I think that is another very important question, and this is actually keeping us engaged in thinking about this. For example,
Yeah.
there is a big difference between self-repairing, or let's say self-engineering in general, whatever that may be, self-healing, self-repairing, all of that, on one component, yeah, one metallic component, and we are trying to self-repair a crack. That's one part. Let's say take a gear and it has lost a teeth. How can you repair that teeth? That's one problem.
Yeah.
And at that component level, that's one type of work. At the moment, we are looking at overall system level, how we can create systems, self-engineering behaviors. Yeah. So that's where we are. In a way, component level is more difficult.
Yeah.
Because that's where we have, and if you remember that program grant proposal we worked on, Ashutosh, that is the kind of early thought about component level self-repair, but building that capability within the machine. Yeah. So that's where the robotic manipulator comes, essentially, with a either laser-based or material deposition-based additive manufacturing. But it needs to be built into the system and can be reactivated when that metal has to be deposited. So that work, in a way, is more challenging. And Sam, do you want to add any more points?
No, I think you covered it pretty well there. I think we've got everything.
Okay. All right. Thank you. Sorry,
Thank you.
Ashutosh,
That's very clear. No, that's very clear. Thank you very much. Thank you.
Okay. Vijay.
Thanks, Professor Rai, for very insightful talk. So I have worked with this group on self-healing materials in University of Illinois, and I spent my postdoc completely working on self-healing. And what I understood and realized is, like, it is very difficult to use these materials for engineering application, especially self-healing based approach. The Bristol people are trying to implicate what they learned from the Illinois people, but the cost of this self-healing material system is really sometimes even more than your basic materials. So my concern is, where do you see like its real application if we are using it for real engineering application, especially weight loading or something like that?
Yeah, I think challenge is multiple. One is cost of the material, as you say, that is quite cost prohibitive in many ways. But second, also to really scale it up in a real life application that's slowly developing, and it's not there yet. So I wouldn't be able to answer exact question for you, but what I can say to you that wind turbine is one example where some of the repair work is already taking place because of the cost of offshore wind turbine repair. Because wind turbine repair is not just the cost of the part, or in this case, let's say replacing part. There is few million on top you have to spend just to access that offshore wind turbine. And that is driving some of this work in that sector. So there are very unique sectors where some of this work is happening. I personally think space is a good area to work on this, where access again is a major problem and very expensive, where this will work. But there are other problems with this. The whole approach needs to be certified if it works, if it needs to be active, useful for regulated market like aerospace. Yeah.
Yes.
And that certification itself is not there at the moment.
Yes, thanks, Professor Rai. Very interesting. And I think you mentioned about coating. And I think coating is the area where self-healing can be really employed, because for that, we don't need to use that traditional capsule-based approach. So another material can be easily used, and it can also be used in wind turbine application, I guess.
Mm-hmm. Yeah, and coating work on composite is already happening in wind turbines, and self-healing and self-repair is useful in that sense.
Yes. Okay, thank you. Thank you, sir.
Thank you.
Can I jump in with a comment about
yes, please, Alan.
Those coatings that respond to friction? There's a lot of work being done in the States at the Wright-Patterson Air Force Base on what they call chameleon coatings.
Mm-hmm.
And these also tend to be the dichalcogenide type, you know, MOS2, tungsten disulfide, etc. And they work well in adapting to, for example, frictional heating and heating effects, and operating in higher temperatures. The big problem is reverse chameleon effect. You know, so it's fine. You can have a coating. It can be adapted to an increase in temperature, but unfortunately, then if you reduce the temperature, it doesn't reverse back. So that's a big challenge for those kinds of, as they call them, chameleon coatings. The guy that's done the work is a guy called Jeff Zabinski. If you want to look for his papers, or another guy.
We will look into that. Yeah.
A guy called Andrei Vovodin. He's now at North Texas University. So they've done quite a lot of work on that adaptive or chameleon. They're not, I wouldn't call them self-repairing or self-healing, but they adapt to the operating environment in a very effective way. And can I just say something about redundancy? Because I hadn't thought about that before, but in a way, you do need some redundancy in some applications. Well, from one point of view, you hope you never have to use, say you put something in a composite, so say something in a crash helmet that will repair if it cracks. But of course, you hope you never use it. So in a way, it's kind of good redundancy that you never have to call on. But I think in the natural world where nature learns, if you think about it, in a way, it's got to put in redundant mechanisms, and I suppose that's how nature learns, isn't it? It puts them in, and if they're not used, then they disappear. So it's we come on to self-learning materials, I guess, would be, and that kind of comes back to what Saurav was saying, really.
Yeah, no, I agree with you, Alan. I think redundancy is a part. question is, what is the optimum amount of redundancy? Because redundancy come with a cost of weight, cost of, cost itself, that it is expensive to have all the resources. And this is where we can differ from biology in designing systems.
Yeah.
So, I'm sorry, Raj, go ahead.
Adrian.
I was just going to try and squeeze one small question in, if that's okay. And it actually relates. It's actually the design process. Mm-hmm. And as we build these capabilities for self-repair, what do you see the challenges of the design process, how it needs to evolve?
Yeah, that's my goal. Before that, we understood better about complexity. We are currently working on design rules that is related to complexity. That should be addressed. And then we need to look at design process, where in the design process we need to introduce these rules. Yeah. As I said, we are working at a whole system level, and we could define what's the boundary of that whole system. And we do need to, otherwise, it becomes too broad sometimes. And to answer your question, I don't know that exactly where it can be introduced. But maybe we should talk about it, Adrian. I'll be delighted to talk to you about this and explore that idea more. What we are focused, Sam and me, we are focused on now is creating design rules which would be relevant for system, and then deriving component level rules. That's what we want to do. But where we apply what, for example, how do we evaluate that design? That's a question I do have in mind, and that's our next stage of research.
The presentation was excellent. It opens up more questions as you start to think about,
that was the purpose.
Yeah, brilliant, really good, and yeah, be great to talk.
Yeah, thank you. So we'll follow it up, Adrian. We'll set up a meeting and have a session on this. Yeah.
One quick thought, Raj, going
Sure.
back to the initial thought that Ash was alluding to about machining problem. So when we think of, let's say, grinding as an example, we have a process and we have a machine. So grinding as a process and the machine tool for the grinding. I could see, for example, technology like electrolytic in-process pressing exists for redressing the wheel, although it's not self-pressing, but we are close to going there towards pressing. What we don't often see is something like self-calibrating grinding machine tool, which is where I think there is a need for stronger research probably. And that then led me to think, to probably ask to have your thoughts. Although we are currently talking about remanufacturing per se, how far are we from self-remanufacturing?
Yeah, I think we have to be a little bit careful that we don't carry on and start adding self in everything. Because, once the new terminology comes, everybody gets excited. I think there is an opportunity, there is an excitement there, but I think we need to try to understand scientifically what's going on. Why these things can self-repair. So some things can self-repair, others can't. Why? And what's the fundamental difference? To be honest, that's what I'm trying to understand. And then once we know that better, how can I apply that to make machines which will then really become useful? And in all of this, my real objective is to reduce maintenance cost. Very basic, going back to my shop floor route, I want to reduce maintenance. I have spent hours, days on dirty machines. Yeah, how can we repair those machines automatically? That's part of the quest I have.
Sure.
Alan, yeah.
Yeah, sorry, I've lost my my hand thing. About 20 years ago, or even 30, I don't know, there was a lot of interest in what they called pterotechnology.
Yeah.
And I wondered what happened to that discipline, which was about planned maintenance, wasn't it?
Yeah. So the whole area of pterotechnology, which I studied, by the way, as a student, yeah, in undergrad and then postgrad in all of this. I come from production engineering background where pterotechnology was a subject to be taught.
Yeah.
I think the way it has evolved, there is some synergy with that. It is kind of next evolution of that, what you could call through life engineering services is. Yeah. But what we are trying to do now is bring in more fundamental understanding of the degradation process itself, using that to develop more predictive capability. That's one difference, which was not well advanced in pterotechnology. And second, design for through life performance. That's the other bit that pterotechnology did not include.
Okay. Some of those people, I know a few people who were into that, they've gone into something that they called e-maintenance. There's a guy in Finland called Kenneth Holmberg who's written about e-maintenance, and I think it's evolved from the work he was doing in pterotechnology.
Yeah.
But I think what was one of the really fascinating things that you had to say was about predicting remaining useful life, because that has to form part of your decision as to whether you maintain.
Exactly.
And what is the cost benefit of maintaining, and is it worth it?
Absolutely. And this is where, sorry, no, you finish first and then I'll come.
All I was going to say is, that's got to be statistical, because you can't predict the life exactly, but you can give probably a statistically reliable prediction with a certain scatter.
Yeah.
And then, you've got to then introduce the effect then of your maintenance. I'm telling you what you already know, but stats has got to come into this, hasn't it, really?
I think it has to, but also in certain areas, depending on the material, depending on what model exists, some of the physics-based model combined with statistical models would enhance uncertainty in those predictions. And that's the way it is going. By the way, e-maintenance is also a very well-developed area. And this is combined with IoT. People like Professor Jay Lee in US and others, many others, have that's another very active area of work where they start essentially from the data coming out from sensors and how do you make sense out of that? How do you decide maintenance? How do you predict life, remaining useful life, RUL from that? That's what their focus is. I'm trying to focus more on the science of degradation, and now based on scientific reasons why certain mechanisms can self-repair or self-heal or self-reconfigure. What is it that we need to do this? That's my fundamental question I'm trying to ask.
Thanks so much, Raj. I think we are closing in close to an hour, and I've seen Ash has left saying thanks for this great presentation. So if there's no other question, then maybe we should really thank you, Raj, for this extremely stimulating presentation. As you can see from the responses, I think the Q&A session went larger than the talk duration itself, which is so exciting to see, really, and really great piece of talk, and we look forward to interacting with you more.
Well, I'll be delighted to discuss further with any one of you, and I know we are meeting Alan, and we will talk, and Adrian will follow it up. Anybody else? Just drop me an email or Sam an email, and we will take it from there. We are very excited about this new work. It's more really fun for us.
Definitely. Any final thoughts, Alan, before we dash off?
No, I think it's an area that's ripe for support, and it's good to see we have EPSRC representation with Elizabeth, and this is certainly a very important topic area for the future.
Sure.
Thank you.
Thanks.
Hi, Elizabeth.
Hi, how are you doing?
All right, thank you. So thank you, everybody, and thank you, Alan, thank you, Saurav, thank you, Pamela, for your invitation. And I really enjoyed the discussion. Thank you.
Thank you very much.
Thanks again. Thanks, everyone.
Thank you.
Yes.
Yes.
Bye-bye.
Bye.
Bye.